So today we have Ricardo Schiappa from Lisbon and from CERN, and the title, as you see here, is from minimal towards Jacques Teitelbaum gravity, resurgence, resonance, and resolvents. So please, Ricardo.
Okay, thanks very much. Thanks for inviting me. It's a pleasure to give this talk. So as Jürgen just said, yes, I'm going to be talking about this sort of path from minimal strings or minimal gravity towards Jacques Teitelbaum gravity. And I'll have 3 R's throughout the talk: resurgence, resonance, and resolvent, and try to transmit why these things are relevant. So this is a lot of work which is in the pipeline and that we're trying to write up to come up. I'm not sure how soon it will be out, but I hope somewhat soon. This is also the first part of a 2-step talk. So there's going to be a follow-up talk in 2 weeks by my postdoc, Paolo Gregory. And so he's going to I'm going to tell you the story of how to go from minimal to JT, and he's sort of going to tell you the story how to go back from JT to minimal. And those will be the key players in his talk, all these people. All right, so let's start up with some motivation. So the motivation for our work is basically how can we get a handle on non-perturbative quantum gravity? So the best shot we have at trying to do that is to use string theory. But string theory is generically defined perturbatively. So if I look at the free energy, which is the log of the partition function, it's a power series in the string coupling. You know, it's the usual sphere plus torus plus 2 torus plus so on. And these guys, these FGs, they grow factorially fast, 2G factorial. So this power series is divergent. How could we, try not to have a perturbative approach to the problem, but a non-perturbative approach? Non-perturbative definition, or I hope to make that a little bit more clear as we go, more interested in non-perturbative construction of string theory. And that would not be the only thing we would like to have. The other thing we'd like to have would be a semi-classical decoding of whatever non-perturbative answer would be, rather than just a black box, something that would, explain human brains, how things are working. And, that should include something which is both perturbative, that is in powers of the string coupling, and also non-perturbative in powers of the exponential of -1 over the string coupling. And the simplest possible example to do this is 2D quantum gravity. So, hence the 2D over there. So I'll be mostly trying to find a non-perturbative definition of 2D quantum gravity. And the simplest possible example within 2D quantum gravity is a setup which is described by the Polynomial equation. So just to set up the stage, and I'll do this slowly, and then we'll review these things in more detail. The way that Polynomial equation describes 2D quantum gravity is the following. And this was, a lot of people were doing this in the 90s. It's the specific heat of minimal strings coupled to a matter conformal field theory, which is a minimum model with C equals 0, central charge 0 matter. And that's the equation. This equation was first come up by Polynomial, I think around 1908. I'm not sure about the date, maybe 1910, something like that. And it's a nonlinear differential equation. They were trying to look up for nonlinear analogs of classical special functions. And it turns out that it has there were 6 of those equations at the time of Polynomial. We're not going to be interested in either 5. In fact, we're going to take off in a direction which is slightly orthogonal to what Polynomial was interested in. That will be clear in the following. And it's quite fascinating that 100 years later, this is actually relevant for this other problem. And so if U is the specific heat, that means basically that the free energy is attained, the second derivative matches U, so in the partition function, that. And so the string coupling is a specific scaling of the variable Z, and you can compute the string expansion and actually verify that in fact you have the 2G factorial, like those numbers are easy to produce. And then you could ask, okay, fine, but that's the simplest possible case. It's got sort of almost trivial matter. Can we have something a little bit harder? Well, there are harder things you can do. So the next two hardest thing you can do would be the Yang-Lee equation. And now, it's the exactly same story. I have specific heat of string theory coupled to matter, which is minimal matter with C equals -22/5. Of course, then there's also the BC and the Liouville that make sure that the whole C is equal to 0. you see that the equation now is fourth order. So the order of the equation is going high. So I'm sort of going in the orthogonal direction to Ponleville. The 6 Ponleville equations are all second order. Still nonlinear, and the story holds. You can compute the free energy, you can compute the partition function, and those are the numbers. And the perturbative series is again asymptotic. These are just, I'm not going to be telling you one by one, the next and the next and the next. I mean, there's a bigger story that encodes all of these people. That will be making more clear why this story is relevant for what we're discussing, which is basically that all these equations can come out of the KdV hierarchy. So if you focus on the example where we're just dealing with a one matrix model, and then we can describe this whole series of minimal or multi-critical strings. I'll be more specific on the distinction between minimal and multi-critical in the following, where we couple 2K minus 1 matter to the string world Shin with K equals to 3, so 4, so forth. These are the central charges. It starts at 0 and then they're all negative. And we can study all this problem. The string equation can be written generically. It's a non-linear order 2K minus 2 ODE. This is the schematic form. I will tell you about these alphas later on. I probably won't tell you about these betas. And you can sort of do the calculation for arbitrary K and realize that perturbative series are always asymptotic. Coefficients grow factorially fast. And then you can say, well, but okay, why don't we just stick with Ponleville? Why are you telling me about harder and harder and harder problems as we go along? Well, because, naively, you could say that K to infinity could be the possibly hardest problem of them all, but not really. So things actually also simplify when K goes to infinity. So it's interesting to observe how these things change as K changes. And K to infinity actually matches something which is quite popular these days, which is Joukiffe-Teitelbaum and dilaton gravity. So this is also a very simple example of 2D quantum gravity, but now in the context of open-closed duality, maybe the simplest. The case which is of interest for JT gravity is the following. We have a bulk action, which has a topological term that's just the Euler number. It's not terribly relevant. Then there's the dilaton coupling there, phi, you see, which sets up R to be equals -2, the scalar curvature. So that guarantees that we're within ABS2. And then there's some boundary terms, which I'm not going to write, but basically that's where the dynamic takes place. The Schwarzian action takes place. But okay, for the moment, it's not terribly relevant. And so if this is a two-dimensional ADS bulk space-time, you would think that within holography, the CFT side would be just simple quantum mechanics. It's actually the story much more interesting, as was made clear a year and a half ago. JT gravity is not dual to a particular quantum mechanical system, but rather a random ensemble of quantum mechanical systems, and that will have a connection with the matrix model. You can also see that the string theoretic expansion is asymptotic for this example. And so we have a bunch of asymptotical problems labeled by K that go all the way from K equals to 2, K equals plus infinity. And we'd like to sort of compute something non-perturbative in all these examples, where resurgence probably is going to play a very fundamental role. So, okay, so again, the motivation that I just said at 2 minutes ago. So I'm interested in studying non-perturbative 2D quantum gravity. I'd like to obtain a non-perturbative construction of all these string theories, which encode, or that they have built in a semi-classical decoding in perturbative and non-perturbative data. So in order to do that, we have to deal with our first R, resurgence. So there will be a trans-series construction behind all these systems. The trans-series, which itself might not be terribly hard to set up, still, in order to define solutions globally, requires Stokes data, in particular, nonlinear Stokes data. This is an infinite set of transcendental numbers, which are generically hard to compute. And so we would need to not only construct resurgent trans-series for all these systems, but also specify nonlinear Stokes data for all these systems in order to claim that we have a complete answer to the problem. Turns out that these resurgent trans-series we're going to be looking at are resonance, so that's our second R, and that is very much built in also into the structure of Stokes data, as I will show in the following. And in order to go through these different values of K and study everything from polynomial 1 through Yang-Lee all the way to Jackie-Teitelbaum, there's going to be a resolvent which sort of underlies these constructions. Okay, so that will be our reduce, reuse, recycle sort of approach to the problem. All right, so that's the motivation. This is what I will tell you about. Let's see if there's time for everything. If there's not time, I'll cut a little bit. So I'd like to start by telling you a little bit about the polynomial equation, the trans series, how you can resum them. Then I will talk a little bit about the resurgence properties of this construction, and in particular, the resonant properties of that construction. And then I will tell you about resonant Stokes data for the polynomial equation. So I gave a talk 2 years ago at the HES for this very same audience about that. And 2 years ago, we did not have complete Stokes data. Now we have complete Stokes data. So there was a number missing. I don't know if how many of you were there and might recall that there was a number missing that we knew numerically, but not analytically. And now we have that. So I'll tell you about that. And then I will tell you how to generalize this story for multi-critical and minimal strings in order to try to put this thing in perspective within the whole KDV hierarchy. Time allowing, I'll tell you a little bit about the technicality of pole locations, which might or might not be relevant to have a broader picture of the story. But I mean, I'm also, in the spirit of this ERC synergy sort of a research program, I'm going to put up some questions that might be of interest to some of you. So I mean, please feel free to then talk to me afterwards if you're interested in thinking and discussing about these things. And so this might be something which might be relevant, we'll see. And then I hope to tell you how to go towards, out of these, let's say, finite K constructions, how to go towards the resurgence of Jackie-Teitelbaum 2D quantum gravity. And as I said, in 2 weeks, so that will be sort of my story. And in 2 weeks, Paulo Gregory will tell you the opposite story, or well, some details on the opposite story. All right, so let's start by talking a little bit about polynomial 1. So that's the equation again that I just showed you 10 minutes ago. And well, it's not too hard to construct a perturbative solution at large Z. I mean, I just set up an ansatz, which has, this is at large Z, which, and the choice of square root and the 5/2 is make sure to guarantee that I have my expansion, my topological genus expansion, string theoretic expansion, and I just plug this guy back in, and I, obtain a recursion for all those guys. And these are a bunch of numbers. So, and they grow 2G factorially fast, as I said, and it's not too hard to generate a lot of it. So that's the perturbative information, which is just easy to get. And then you may ask, all right, good. Now let's go non-perturbative. So the first thing that I would like to see would be stuff which is not powers of GS. Remember that GS is just a scaling of the Z variable, -4/5 or whatever it is. But now let's plug in some exponentials. And if you plug exponential ansatz into that equation, then because it's a second order equation, you basically get 2 instanton actions. Those are the 2 values of the instanton action. And that means that, well, that's a long story that I'm making short. That means that the trans series solution to this problem is actually a 2-parameter trans series solution. Well, I mean, it's almost obvious that it has to be 2 parameters because the polynomial equation was second order. And so there, these 2 parameters, sigma 1 and sigma 2, are sort of parametrizing boundary data for the second order differential equation. Here I have went back to GS variable just to make the formula slightly less cluttered. There's the exponential terms, and you see that I have n minus m there. That's associated to the fact that, oh, sorry, wrong direction. Associated to the fact that I had a plus and a minus over there. So that's the exponential term with that instanton action. And then I have a bunch of perturbative sectors. So these guys, they're attached to powers of the log. This is just basically a finite summing log. So the logs actually, they're not even independent as I've just said here. So they just easily can be taken care of. And so what's encoded in these phi's is basically asymptotic sectors. And now what I would have to compute would be all those numbers in black. Beta here is some starting order. So not everybody starts at order 0. And so, I already computed for you a bunch. So this would be sort of the, let's say 0, 0 sector. Those are the numbers. And generically, you compute a bunch of those numbers. And we've done this quite a few years ago and computed a lot of these numbers. And you could ask, well, okay, good. So how do you know that that's real in the sense of effective solution to the problem? And this is, complex generically. Well, one way to look at that is by looking at asymptotics. So we can use this large order resurgent relations to study the asymptotics.
Sorry, Ricardo.
Yes.
Just a question. So
sure.
I didn't quite understand, the sigma 1 and sigma 2. I mean, how do they relate to the original equation?
Okay, let me repeat that. I'm sorry, that was not clear. So the original equation is no, it's fine. So the original equation is a second order differential equation. So that needs two boundary conditions or two initial conditions to specify a solution. So if you want, you can think of this for arbitrary sigma 1 and sigma 2 as the general solution to the differential equation. And then when I fix sigma 1 and sigma 2, I will have a particular solution to the equation, to the differential equation. And so I do need two parameters if it's second order.
Yeah, okay, thank you.
Yeah, sure. And please go ahead, ask any questions whenever. There's really no problem. I mean, I prefer that I have lots of questions and I just finish the talk halfway than the other way around. Okay, so what I was going to tell you is how can we check if this is actually a good resurgent solution, given that we compute a lot of these numbers, but we don't compute them all because the equation is nonlinear. So that means that I have to generate numbers recursively. I don't have a closed form expression for the arbitrary UG and NEM coefficient. So one way to check whether that's true is to look at, as I was saying, this large order behavior of perturbation theory. Well, here I've written F, but it could be U, it doesn't really matter. And Resurgence tells us that the 1 instanton, the 2, 3, 4, 5, 6 instanton, so on, sectors, they control the large order growth of the perturbative sector when G is very large. And here's an example of how that works. So I have the leading factorial growth. Here I'm not worried about the 2G factorial. I'll say a word about that in a poem. So there's leading factorial growth. There's subleading exponential growth, which is controlled by the instanton action. Then there's Stokes data. And here I have the 1 instanton sector, the 1, 2, 3, 4, 5, 6 loops around it. Down here I have 2 instanton contribution, exponentially suppressed as 2 to the minus G, and so on and so forth. And you could ask, is this the correct asymptotics of that problem? Well, it's actually not. Correct asymptotics of that problem is slightly more intricate. And it's associated with the fact that I actually have an n minus m there. And this is what it looks like. So this is the first hint of resonance. I'll tell you more about resonance. Is that there's a contribution from an A and a minus A. And again, that's sort of almost obvious because that's what I computed for you 3 slides ago. And the contribution of these A and minus A, they came symmetrically. And so this is a characteristic that will be very clean in all our problems. And so here I'm just looking at the growth, the leading growth. So there's 3 dots there. You cannot see it, it's blue on blue. But I'm just looking at the leading contribution. And so I have, in fact, the factorial growth, and then there's an A and a minus A. And these things make sure that the 2G factorial growth will eventually appear. And so, and all these problems are going to have this characteristic asymptotics. These can then be checked. So basically, I have a bunch of these numbers. They're all rational numbers, and I can check whether resurgence, in particular resonant large order resurgence, can, with formula like this, can predict those guys there. And here's a numerical check. So if you go to G up toward the 30 and you include 1, 2, 3, 4, 5, so on, 9 instantons, what you're going to get is going to be 70 digits of precision between the rational number that comes from just the recursion and what Resurgence tells us. And this sort of makes us believe that the solution we have is very clean. Yes?
I have a question about the formula you had for the series, the trans series.
The trans series.
Yeah.
Yes. Go ahead.
Yeah, just above. Yeah, when you write down the sum over n, m, and k, so you have in mind that the transmonomial, you have in mind the transmonomial ordering, meaning that I shouldn't consider the order of sum over n and m, but rather first have a sum over positive exponential and so on?
So from the point of view of the sum itself, not really. I mean, the transmonomial ordering is only relevant when you're going to do resummation. I'll tell you a little bit more about resummation in the next slides.
But so is it important for you, the ordering of the sum signs or not?
Not really, no.
Not really?
No.
Okay. Can you exchange them? Or
I'm sorry, I didn't understand.
Can you exchange the ordering or not?
Yes, I will also, yes, I will probably also talk a little bit about that.
Okay.
It actually can be very useful. Let's see, if there's time, it connects to this problem of the poles of strongly. So the final slide here on the train series, also to answer a little bit this issue of the resummation. So how would I now, I mean, I validated my train series. I say, okay, it looks good. Let's get numbers out of this. What do I do? Well, I have these phi and m's. They're all asymptotic series. So the way that, to get a number out of that is to do Borel resummation. That's Laplace integration of the Borel transform of those sectors. And then I still have to plug these guys, once I compute them, I have to plug them into the train series. They're sort of the building blocks of the train series. And then I have to do, let's say, a Cal summation where I have to sum over all these instanton sectors. Now, it turns out that if you construct a solution like that, it only holds in Stokes wedges, the sigma 1 and sigma 2. They will have the value they will have in between, on the Borel plane, lines of singularities, lines of Stokes lines. And so whenever I need to cross one of these Stokes lines, I will need Stokes data. So, I mean, so far, the answer is not complete. The other thing is that train series are resonant. There's an n minus m there. And in particular, when n is equal to m, all the diagonal non-perturbative sectors have the same weight. So I also have to sort of do the resummation along these directions of resonance. Okay, say a little bit more about that. Okay, so let's see a little bit more about resurgence and resonance. And in order to do that, let's just for a moment step back and consider a general problem where I have k instanton actions that are organized into a vector. And I have a train series that I organize in the way that's written here. So there's now k train series parameters. There's an inner product there with that instanton action. And then there's a bunch of asymptotic sectors with those coefficients UGN. And okay, there could be also betas here with the starting orders. I was lazy and I didn't write it down. All right. How does this train series translate to the Borel plane? Because, I mean, eventually I'm interested in computing Stokes data. Well, the location of Borel singularities, given the train series, is not so hard to find. I mean, it's just, there's a projection map basically dictated from the instanton action, which is this one. There's just inner product, where, of course, now I start in the Z lattice, not in the N lattice of the train series, because alien derivations allow me to move backward on the train series. And so this is where singularities are. And what does the Borel transform look like near each of these singularities? Well, here I'm looking at the Borel transform of the nth sector around its elf.a singularity. And if it is a simple resurgent function, then the singularities are basically poles and log branch cuts. I'm not going to talk about poles and just ignore them, but they're always there. And so this is the log branch cut singularity. Of course, there's regular terms here that I'm not writing, but I'm just looking at the singular term. So there's a log cut. And in front of the log cut, I have, as we say, the resurgence of the N-Split-L sector up to a coefficient, that's the Borel residue. This is the things that we would like to compute, Borel residues or Stokes data. Resonance makes this slightly trickier. So here I'm trying to explain resonance in a plot. So here I'm having a 2-parameter train series in these two drawings, and this is the 3-2 sector of that train series would be train series. I mean, this could be very much Paul-Levé. In fact, this one could be Paul-Levé 1. And what I'm drawing in black are the possible singularities in the Stokes lattice. Because they're allowed by backward motions of alien derivatives. And then what I'm drawing in green is the projection from the train series lattice to the Borel plane. So this is sort of a one-dimensional complex Borel plane. And here I have a non-resonant map where the kernel of the projection is basically trivial. And here I have a resonant case where you can see that many possible Stokes data fall on top of the same singularity, and I will need to unravel these numbers in order to see them properly on the lattice. And as I said, actually, I said this a little bit earlier on, all these examples are resonant because they have to encode both open and closed strings in the same block. So how would we go about to find these numbers? Well, there's sort of two ways to think about them. You can look at the Borel residues, which appear there as the proportionality factor of the Borel transform. Or you can think about Stokes vectors. So these are the alien derivatives. So this is exactly the same statement. Let me just, so there's the Borel of the nth sector at the alpha singularity. This is the resurgence of the nth plus L. And here we have, so that's the nth sector, alien derivative at L dot A. This is the resurgence of n plus L. And now the proportionality factor is that Stokes vector. But I mean, basically, it's the same. The Stokes vectors, they basically occupy pretty much all quadrants of the ZK lattice except for the first quadrant, and you can relate them. So here I have Stokes vectors, and you can relate them to Borel residues. So you choose which ones you rather work with. Some appear at the level of basically the Stokes automorphism, and the others appear at the level of alien derivatives. It's basically the same. So I need to disentangle basically all these guys. And they, so here's my Stokes vectors for a two-dimensional problem. They occupy, these are the non-trivial people. So they go slightly here in the X direction, slightly here in the Y direction, but this whole first quadrant is pretty much clean of them. And so they sort of occupy this lower left-hand side. And we like to compute all these vectors in order to have complete Stokes data for a Polynomial equation. Why is that relevant? Of course, because of crossing Stokes line. So if here I'm on the Borel plane and I have a Stokes line, so line of singularities, the left and the right Borel resummations relate via Stokes automorphism. In the simplest possible case where I just consider the forward direction. So let me just consider that guy. That guy is actually pretty simple. It only has an X component. Here I could have written X. I don't have to be in the general case. And then the Stokes automorphism simplifies a lot in the sense that Stokes phenomenon amounts to a jump of trans-series parameter just by that S. Of course, in other directions, it's more complicated. Let me not worry about writing down Stokes automorphisms, but just say that I need to know all these guys if I can do all, if I want to do all possible Stokes jumps. So let me tell you about what is the resonant Stokes data for the Polynomial 1 equation. The trans-series is resonant, once again, our second favorite R, A minus A, and the kernel is non-trivial, is the span of the 1-1 vector. And this means that alien derivatives actually have a very, very symmetric reorganization. Let me actually show you immediately the plot. So if this is my building blocks of the trans-series, my asymptotic sectors of the trans-series, this direction, this diagonal direction is the direction of the kernel, and alien derivatives along blue and red directions are basically very symmetric. So that's the formula which I have written here. And so basically they're organizing along these directions. When they project out onto the Borel plane, I need to disentangle Stokes data that would be associated to all these people. For example, that's all on top of that. So the logs that appeared earlier in the trans-series solution to Polynomial partially are allowing for this disentanglement of these resonant sectors. All right, so how do we compute them? First of all, we actually only have to compute half of these guys. So there's the red and there's the blues. I actually, you know, if I compute the blues, I know the reds. Because there's relations because of resonance. So if I'm here on the 3-3 sector and I look at the alien derivative there in solid blue, it's just basically given by those quantities in dashed blue, and the same for the greens and the reds. So the solid lines give you the dashed lines. And so there's a way to relate Stokes vectors in what we call forward and backward directions. So we just basically need to compute half of these guys. And well, we'd like to know a lot of numbers. So there's no first principle way to compute these things. So the first thing, of course, we try is to just do some numerics and get some numbers and try to see if we can populate this lattice a little bit. And so now I'm hopefully, some of you were at the HES 2 years ago, and I was telling you about this, and I'm recycling 2 or 3 slides from back then in the spirit of the 3 hard talk. And so 2011, we did some numerics. We looking at asymptotics, and we got a bunch of numbers, not a lot that were coming from asymptotics. And then, mainly what I was telling you 2 years ago at HES was that we had come up with, well, not mainly, but half of the talk at HES 2 years ago was about how we had came up with a new method using residue calculation, numerical method to do residue calculation to compute more of these numbers. And we actually had a whole lot more of these guys, mainly along the diagonal, the two first non-trivial diagonals, not so much off of the diagonal. And I also discussed this a little bit back at AHS, that the precision is actually, drops very quickly with computational time. So you can see here that if I just go down the main diagonal, I can get a pretty decent precision on computing these numbers, although the timing to do that starts to be on the order of weeks. But the precision drops very quickly as I move off the main diagonal, and the time increases a lot. But anyways, so those are the numbers that we had found numerically and that we would like to understand. So can we say something? So, I mean, I could show you all those numbers, but let's maybe I did a bit of that back at the HS, but now let's just think on what could we say analytically about these numbers. So again, if we know the blues, we know the reds, let's try to find some of these guys. The first thing that is actually quite peculiar that you notice is, and this is observed numerically, and then it's conjectured to hold true, is that the commutator of two alien derivatives closes into an alien derivative. This need not be the case. Generically, there's no reason why that happens. But when that does happen, that means that there's this interesting relation between, here, of course, we know the proportionality factor. I'm just not writing it because it's not particularly illuminating. But there's this relation between Stokes vectors. And this is observed to hold numerically for pretty much all the data we computed. And so we can just conjecture that it holds true for basically any possible data we could have. And that means that Stokes vectors have this form. So they sort of have a simple vectorial form. And then there's a proportionality factor that needs to be determined. And it turns out that all these guys are reconstructed from Borel residues coming from a guy in the main diagonal to a guy sort of, let's say, on the boundary of the train series. And so things start to be a little simpler. So this is what starts to look like. I mean, now I just have to compute these n factors. Again, if I know the blues, I know the reds, but the vectorial structure is quite simple. And then, you have a bunch of very good students that stare at these numbers for a long time, and they come up with amazing relations that actually made it, for this project to go through. So if we walk down the first diagonal, let's say this is the first diagonal. If we know these first two guys, then we can predict all these guys. So you see, there's the ratio of those first two guys that's appearing there, and they also appear there and there. And then we can go down the main diagonal. And if we go to the second diagonal, can you see? I mean, it's not so, just look at these numbers. And they became twos. So there is clearly some structure there. And what happens if you go to the third diagonal? Threes. So, I mean, there is some clear picture here, some very clean patterns going on, where if I know the first two guys, then I can predict everybody else. Then it turns out that the first guys actually are dictated by those guys as well. So turns out that there's relations to go down. And so the infinite set of Stokes data amounts to two numbers. There's a number that was computed by François David in the 90s. And there was another number. And so this is sort of to wrap up the talk that I gave at IHS 2 years ago, that we had basically, decimal place digits. I don't remember how many I showed you, 10 or 20 or whatever. And there was no number. And we had tried a lot. And, just right after the summer, we got the last thing that was missing was the Euler-Mascherani. And so those two numbers now can basically pretty much describe you all using relations like this one, which involve, pretty transcendental numbers and tell you everything about Stokes data for the Polynomial equation. This also allows for conjecture on asymptotics. So there's sort of some closed form asymptotics that leads to equations that pretty much can allow us to find generating functions for all Stokes data, which means we can write down arbitrary Stokes automorphisms for all these problems. So we wanted to compute these guys. They had this vectorial form, and here's the numbers. We know analytic expressions for all of them. All right, so that closes the Polynomial story. Oh, no, actually, I had one more slide. This is what they look like when you go down the diagonal. They're just basically a hump. So they do little humps as you go down. That's what these numbers look like. So that closes the Polynomial story. And so in this ERC synergy spirit, so now we have two questions that, I mean, I just started thinking about them. So we actually have not a lot of insight. And if anybody wants to talk, discuss, I'll be happy to. So one thing you could ask is that now I have full nonlinear Stokes data for the Polynomial 1 problem. That's done. Can one set up some sort? So that means in particular that I can write down Stokes automorphisms for the Polynomial 1 solution. So maybe there is some sort of nonlinear Riemann-Hilbert problem that would, compute for you directly the Polynomial 1 solution. And if that would be the case, that it might also be, that's another question, that this nonlinear Riemann-Hilbert problem would have something to say about the location of the Polynomial 1 singularity. So these are two questions that we're sort of starting to entertain. So really not a lot, not a lot matured yet, but if anybody wants to discuss, please feel free to join in.
So just a comment, Ricardo,
yes,
about
please,
this.
Go ahead, please.
But I don't know if it has any bearing actually, but I mean, there's a well-known correspondence between Higgs bundles and then Penn-Leray equations via Hitchin's work. And does that shed any light on these two questions?
Again, I have no idea. I mean, the studies are very naive, not very matured at all questions, but I'll be very happy to talk more about this with you. So maybe there's something interesting there.
Yeah, okay.
All right, so that was Polyvim. First half of the talk done. Second half, let me try to tell you how we can do all these things for, higher string equations, which means having more complicated. So remember that Polyvim 1 is SQL 0 matter. So that means that the matter that we're adding to our string theory is almost trivial. And it's already a very complicated problem. So what happens as we add more complicated matter, higher case? So let me just remind you again that we had 3 R's to discuss. I only talked about 3 R's yet. So we're trying to understand non-perturbative 2D quantum gravity, a non-perturbative construction, which has a semi-classical decoding built in. That means that it's got to be resurgent. And we found out that it's also resonant. Hopefully you sort of believed or were convinced by what I told you in the past half hour. And Stokes data is quite complicated, but can be computed. So the last R that we need to talk about is the resolvent. So how can I sort of find the more complicated hierarchy of string equations inside or in a similar way to what we've just done for Polyvim? Well, that goes back to 1975 to quite spectacular work by Gelf and Dickey, where they did the following, just, one slide on that. So I'm not certainly doing justice to their work. But you consider one-dimensional quantum mechanical problem with an arbitrary potential, U, with conventions, adequate conventions for H bar and the M, so that the Hamiltonian looks quite simple. And then you consider the resolvent operator of this Hamiltonian. That's basically just the inverse up to, well, lambda encodes the spectrum of the problem, of course, and the integral kernel. So if you look at the diagonal of the integral kernel, so when X and Y are the same, it turns out that the diagonal of the resolvent has an asymptotic expansion in inverse powers, half integer inverse powers of lambda, where these RLs, these coefficients, are polynomials in U, the potential, and its derivatives, and they actually satisfy a linear recursion. So it's not so hard to generate a lot of them. And you could say, okay, that's, from a quantum mechanical point of view, this is actually very interesting because, I mean, I didn't specify my potential. So it's quite fun that I can say a lot about the resolvent. But what's actually quite even more remarkable is that this precisely relates to the string equations that we've been looking at in particular, two of them that I already showed you, and all the others that I did not show you. So when we look at the first case, k equals 2, then that's the Galvanic polynomial that you can compute. And up to a factor, what you get there is the homogeneous side of the polynomial equation. So you know how to find the string equation of the 2, 3 multicritical theory. Remember that we were organizing these theories in 2, 2k minus 1 conformal method. When k is equal to 3, that's the next guy, that's what the Galvanic polynomial looks like. And up to normalization, you get the homogeneous side of the angle equation. And so this is actually something generic that was found back in the 90s, that I can write down for the 2, 2k minus 1 problem. I can write down the string equation. There's a question. I just saw, I'm sorry, but please unmute yourself and ask away.
Yeah, thank you. Sorry, could you go back to the previous slide so I could take another look at what the K means?
No, wrong direction. Hang on a second. Oops. This one?
The one with the definition of the Galvanic potentials.
This one?
There you go. Okay. So, sorry, could you point out? Okay, there's a K on the next slide. Where is the K?
There's a K on the next slide. Oh, I'm sorry. This is just I changed notation. So the K would be the L.
Okay.
Okay. I'm sorry. Is that clear? I apologize.
Yeah. If you don't mind, is it okay to just take a harder look at this definition? Because I don't know about other people, but I'm not familiar with how these things are defined. So this is an expansion of the diagonal of the resolvent.
Yes.
So R lambda, okay, that's R lambda XX.
Yes.
And I see. Okay.
Is the slide clear, or should I answer some question? I'm not sure.
I guess, okay. If it's off topic, we can do it later. It's like, why, for example, is there a reason I should expect that this sort of has this kind of expansion? The diagonal has this kind of
the asymptotic expansion. Well, you can actually show it, and you can see in examples. I mean, even if you use such a simple potential as, I don't know, 1 over x squared potential, you can immediately see that these polynomials will give you factorial growth. So this is not very hard to check. There's also, if you go back to the Galvanic paper, there's also a generic proof for arbitrary potential. But I mean, when you specify a single potential, it's very easy to see that all these things are asymptotic.
And that's, like, naively, I would think that if I shifted the Hamiltonian so that the eigenvalues were at a different place, then the expansion that the lambda would sort of, the diagonal of the resolvent would blow up at a different place. But this seems to be saying that it always blows up at lambda equals 0, regardless of whether you shift the Hamiltonian.
No, that's just the adequate expansion. So the way that Galvanic construct is by doing perturbation theory in terms of the free particle, basically. That's also the reason for the square root. So okay. This is just the way that the Galvanic expansion is set up.
Thank you. Okay.
All right. Okay. Anyways, I mean, we can talk more about this after the talk. If this is just a detail for the point of view of the talk, but I mean, we can certainly go back to that if you want. Just I'll be available for that for sure. Anyways, so as I was saying, now we can write down string equations for the arbitrary K theory. That's just the normalization, which is adequate. That's the Galvanic RK or RL. I'm sorry, sometimes I call it a K, other times no. And Z, of course, will be related to the string theoretic, to the string coupling GS, and it relates with different powers, different scalings for the different problems. And these are again the F23 and the F25 free energies that I showed you in the first slides, where I was trying to motivate what I wanted to do. And well, we can now compute arbitrary these things. All right. So that was, okay, let me just say one more thing. So, and this, of course, is just perturbative expansions. I'm sorry, I didn't want to scratch the numbers. These are just perturbative expansions that they grow 2g factorially fast. So the question that we have next is, in fact, it's written here. The question that we have next is, what is the non-perturbative content of all these multicritical string equations? So it's actually not terribly hard to guess, because we know that string theoretic non-perturbative effects should go as exponential minus 1 over GS. These are basically D-brane contributions, which in terms of the variable Z for the arbitrary K guy can be written like that. That's just the scaling that Z has to satisfy to give you back GS. So the first thing you could guess is that, well, maybe there's a 1-parameter trans-series for the order K multicritical theory. That should look the way that I've written here. So there's just some adequate Z to the 1 over K normalization. There's a 1-parameter sigma. Then there's the instant on action 8. There's the basically the strength of non-perturbative effects a la Schenker. If you want, there's a characteristic exponent beta, or if you want a starting order for the genus G, and then I would have to find all these guys. So this is a very reasonable first guess. Of course, it can't be the whole story, right? Because I still didn't say anything about resonance, or the fact that, by the way, maybe I should have been more explicit, is that the kth Galvanic polynomial is differential in 2k minus 2. I'm sorry, I should have written that there. So that means that a single transeries parameter will answer the solution of a 2k minus 2 order differential equation. But okay, but it's a first guess. So let's see what we can do with it. If you plug this in back into the examples that we already discussed, so only if you want, without surprise, oh, there's the plus and minus, the instanton actions I have. That's the beta 2.5, and you can also, so I've written just for completeness, you can compute here the one instanton expansion around the plus instanton action. What happens when I look at the next guy, at the 2,5 multi-critical model? Now there are 4 instanton actions. So this plus minus and this plus minus are independent. Okay? So they're not correlated. So I have 4 different instanton actions, and they come in symmetric pairs. Beta is 1/2 again, and I can also, here by plus I mean I choose that sign plus, and I choose that sign plus, which I need not have to do, and you can also compute this expansion. So can I say something generic about this? Well, the answer is yes. So it's you can already start guessing what's going to happen. It turns out that if you write the instanton action with an adequate normalization, then this rho is a root of a polynomial equation. This was already known back in the 90s, a la WKB. And now we have shown that the transeries gives exactly the same result. This is not a big surprise. And so this is the polynomial, and rows, the roots of this polynomial, will give you the instanton actions. By the way, the characteristic exponent is generically beta equals 1, but that's just a comment. So the polynomial is degree 2k minus 2, which is associated, of course, to the fact that I have, as I just said, a 2k minus 2 order differential equation. So in fact, I should have 2k minus 2 instanton actions associated to 2k minus 2 transeries parameters, parameterizing boundary conditions or initial data, whatever you want to call it, for that differential equation. But it's a polynomial in rho squared, to be more precise. So the k minus 1 instanton actions appear alongside their symmetric pairs. So all these problems are in fact resonance. Let me show you what the generic problem should be. The order k multicritical theory should be a 2k minus 2 parameter resonance transeries. Resonance coming from this fact here. That's what the transeries should look like. So I should have 2k minus 2 parameters, an instanton action vector which has k minus 1 guys and minus k minus 1 guys, and then asymptotic sectors where I would have to find those coefficients, and you can find them for a lot of problems. And resonance means that the kernel of this thing is different from 0. So now you could ask, okay, so I have the transeries, so I can say something about Borel plane of these problems. So here's the Borel plane of polynomial 1. I have plus and minus instanton action. So here are multi-instanton sectors, and you see that these are Stokes lines, lines of singularities. And this is the Youngly case. So I have my 4 guys here. I have my directions of multi-instantons and my Stokes lines. And they're sort of, unspoken little friendly competition here in this ReNewQuantum seminars to who has the coolest Stokes lines to present. So here's my very humble attempt of cool Stokes lines for the k equals 20 and the k equals 41 theories. So you see how singularities organize themselves on the Borel plane, how multi-instanton singularities organize, and how Stokes lines organize. And the reason why I chose an even and an odd number is because in the even case, there's a singularity on the real axis. That doesn't happen in the odd case. All right, so very nice. We have all these guys, but we still don't have Stokes data. How can we get Stokes data? So in order to get Stokes data, we go back a few years when we're looking at matrix models. So here's the emission 1 matrix model. M is an n by n matrix with polynomial potential V. And the nth large n limit free energy has an asymptotic genus expansion. All these can be, well known by now, can be found out of the spectral curve of the matrix model. Here's the spectral curve for the one cut case with cut between A and B. And there's a polynomial, well, when the potential is polynomial function M in front of it, which is known as the moment function. And it turns out, so this work we did back in 2007, that you can actually compute non-perturbative data out of the spectral curve alone. So if you use the so-called holomorphic effective potential, which is basically the primitive of the spectral curve, that's what appears at leading order at large end in the matrix model. Then the instant on action is basically the difference, sort of a difference of energy between the endpoint of the cut and the non-trivial saddle associated to this integration that should occur outside of the cut. So that's what the X naught is. And so you can compute instant on actions, and you can also compute the one loop around the one instanton, which gives you the Stokes coefficient. So there's a formula for these things, given a spectral curve. So the question that you could ask is, okay, do I have spectral curves for all these multi-critical problems that I can actually compute Stokes data for all of these problems? There's just a little technicality that I want to tell you, that there's actually two different backgrounds that people usually consider. So I've had this a little bit under the rug. I will keep this a little bit under the rug. But I'll just make the comment anyways, that there's two closed string backgrounds that people usually consider. They're associated to turning on KdV times in this KdV hierarchy of the Galvanic polynomials. So there's the so-called multi-critical background, where basically I'm sort of from the point of view of the world sheet theory, I'm turning on the lowest dimension operator. And that means that I only have to choose one Galvanic polynomial to look at the string equation, but the spectral curve itself will be a sum over Chebyshev polynomials. Well, the sum is the sum which is here. Then there's another background, which is known as the conformal background. From the point of view of the world sheet theory, I'm just turning on the bulk cosmological constant. So this multi-critical background is sort of the one that naturally relates to the matrix model calculation. This conformal background is the background that naturally relates to world sheet calculation, in particular to the Seibert's analysis of minimal strings with ZZ and FZZ T-branes and so on. Now the string equation is more complicated because I have to actually turn on pretty much all the Galvanic polynomials lower than K, but the spectral curve is much simpler. It only has a single Chebyshev polynomial appearing. So anyway, so we can do the calculation for these two curves. So let me just tell you that this is the 2,5 multi-critical. There's two non-trivial saddles which are complex. I can compute instant on action. I can compute Stokes data. I can do the same for by the way, this is the conformal, this is the multi-critical holomorphic effective potential. So that's where the saddle would be. This is on the complex plane. It's a ray on the complex plane. And I could do the same for the conformal background. Conformal background is actually interesting because the non-trivial saddles are now all real. So I can compute instant on actions. I can compute Stokes data. What you should, and that's what the holomorphic effective potential looks for, the conformal background. So now the saddles are both real. So you should notice that I'm only getting half of there's a plus minus there, huh? Half of the instant on actions that I should get. So the spectral curve is not seeing resonance, but it's, there's pluses and minuses. So it's computing for me Stokes data. And you can do this generic. So again, I think my time is almost done, so let me just try to start wrapping up. So again, in this ERC spirit, the first question that, the synergy spirit of the ERC, the first question I would have is, can we compute the full nonlinear Stokes data for all the KdV hierarchy, just like we did for polynomial 1? I think the answer is probably yes, but thinking a little bit about this. Then the two naive questions that would be interesting to discuss more. Can we set up nonlinear Riemann-Hilbert problems for generic multi-critical or minimal string solutions, and would they relate to singularities? So very unmatured question, but I would be interested in exploring first within the context, within the context of this ERC. And the final question is, how generic is resonance? Because it's clearly appearing, let me just show you that plot again. I mean, this is clearly, these plots are all completely symmetric. So resonance is clearly a feature of this problem. And so I will say nothing about that today, but maybe sometime soon we're looking at this and maybe we'll have some answer for that. All right, so I'm sorry, my time is sort of running up, so let me not tell you about locations of Paul-Levé poles. This is basically the reason, you know, that Paul-Levé was interested in this, and later Boutreau. They have singularities. All these KDVRQ people have singularities, and maybe they all relate to this problem. But, you know, I think it's probably best that in the last 5 minutes, I tell you instead about the relation to JT gravity. So we've been looking at, sorry, did I jump 2 slides? No, just 1 slide. We've been looking at this order K problem. And you know, the natural question that you could have is, well, what is the K to infinity problem? Already in the beginning of the talk, I already sort of hinted to what it could be. And now let's see what it is and what else it is. We make this clear in a couple of slides. So let's go back to JT dilaton gravity. So remember that there was a topological term, and then there's a dilaton term that makes sure that we are in ADS2, and then there's boundary terms where you have the Schwarzian action and you know, you have the non-trivial dynamics. The natural observables in this problem are macroscopic loop operators. They're sort of creating asymptotic boundaries with some length beta. So, you know, I should have thought a plot maybe here, but anyway. So you have these boundaries which are created where the non-trivial dynamics occurs. You may have seen these plots before, and these macroscopic loop operators look like that. The disk partition function was computed, I think, 3, maybe 4 years ago already by Stanford and Witten. It's 1 loop exact, and that's what it looks like. And you know, in the holographic context, this cannot be the full story. You can compute the density of states out of the partition function, just you know, Laplace integrate, whatever. And you find a continuous spectrum, which is not holographic. Holography would ask you for a discrete one. And so the solution to this problem came in 2019, spring of 19, where by Satchenker and Stanford, who told us that in order to make holography precise, we actually have to sum over all higher topologies. And that means both genus and boundaries. So I'm not just looking at the disk, but I have not only at the disk, but I actually have to look at a whole more people. So I basically have to look, let's go straight to this formula. I'm not looking just at the G equals 0, N equals 1 contribution, but I have to look at all genus G and all N boundary problems. And I have to sum all of them to have the correct holographic correlation function of these macroscopic loop operators. The coupling here in spacetime, G string, is exponential of minus S naught, where S naught is basically that term which is there in front of the Euler term. These guys can actually be generated recursively via Weil-Petersen volumes. So, I mean, if you know the, let me again, maybe make some plot. If you know contribution of Weil-Petersen volumes, then basically in order to compute these guys, all you have to do is glue trumpets to all of these VGNs. So this would be the Z trumpet. So you probably have also seen this story before. And the reason why, or the underlying reason why this is actually, the holography is working very well, was actually done by 2 of our collaborators in the RC, is that the recursion of Weil-Petersen volumes due to Mirzakhani is actually matching the topological recursion of a very specific matrix model. And the matrix model, Spectral Curve, is the one that I've shown you here. So I think my time is probably up in a minute, but if I could just have 1 extra minute, I should be able to finish.
Sure.
This is the spectral curve of the JT matrix model. And it turns out that you can obtain the spectral curve by looking at the conformal background. The spectral curve of the conformal background that, recall, had a single Chebyshev polynomial. So here zeta is the uniformization variable that I'm using. So I'm writing the z x as the second Chebyshev, y as the 2k minus 1 Chebyshev, and an adequate k to infinity limit produces exactly that spectral curve. And this has been, you know, a topic which is very popular in the past 2 years. And then you can, you know, sort of, so that's the arrow that I've sort of discussing with you in this talk. And Paulo will tell you about the opposite arrow as well, that you can also think of the minimal string as a deformation of JT gravity. Now, there's a lot of interesting non-perturbative information in JT gravity as well. I think Paulo probably will tell you a bit more about this in 2 weeks. That this is the holomorphic effective potential for JT. So you see that there's basically a lot of non-perturbative instanton sectors. There's basically infinite instanton sectors with instanton actions that we can compute and with Stokes data that we can compute. Very likely this is a resonant problem. We haven't been able to show that yet, but I mean, I personally don't have a doubt that that will be the case. And so there's certainly a lot to see here. Just to finish, this is actually not the only background that we can consider, not because besides the conformal background, there's also the multi-critical background that we discussed. The one that where you actually have a sum of a lot of Chebyshev polynomials. And when you look at the k to infinity limit, what you get is this spectral curve, where that d is the Dawson function, which relates to the error function. So this is a sort of a different limit. It's certainly non-trivial at the non-perturbative level. So here's a bunch. So these are the finite k singularities that I already shown you. Well, I'm just showing you the first quadrant. And those are the Dawson singularities. So that's certainly non-perturbative, non-trivial. And so you could ask yourself whether there's, in the same way that, you know, the previous case, this curve was associated to JT gravity, whether this other curve is associated to some sort of Dawson, quote unquote, dilaton gravity. And whether there's an enumerative problem as well. I mean, again, JT gravity builds upon the Weil-Peterson volumes. And you could ask, well, does Dawson gravity would build upon other sort of enumerative problem? That was one possibility. A more likely possibility is that it will still build upon the Weil-Peterson volumes, but the trumpet itself, it would be different. So there will be the JT trumpet and there will be the Dawson trumpet. But anyways, so these are questions that we're addressing right now about this. So I think my time is up by 2 minutes. So let me just wrap up. I think I hopefully convinced you that we can use this technology of resurgence to look at Polynomial equation. And for that one, certainly I've computed the full nonlinear Stokes data. I hope I've also convinced you that this can be used to go down the KDV hierarchy, look at multi-critical backgrounds, look at conformal backgrounds. I gave you a partial description of nonlinear Stokes data, but think that probably we can get a full Stokes data. I didn't tell you about the relation to singularities, but well, I think at some stage the slides will be uploaded and you can take a look at them. And it seems to be that I also convinced you that this technology is extendable to JT gravity and other sort of dilaton, ADS2 dilaton gravities. Of course, hopefully what's underlying this whole problem is some sort of non-perturbative partition function that would look at all these problems, not only what I've described for you in this talk today about these double scaling limits, but maybe possibly also encompassing matrix models and topological string theory alongside the resurgence of all 2D dilaton gravities that you obtain in the limit where k goes to infinity. So I'm sorry I ran a bit over time. Thank you very much.
So thank you very much for your talk. Excellent. Questions?
May I ask a question?
Sure.
Yeah, your index k of the minimal strings, I mean, you take it to be integer. I mean, can it be continued to non-integer?
Well, I mean, from a physical point of view, that wouldn't make a lot of sense because, I mean, it would not be relating to a minimal model of conformal field theory. From a mathematical point of view, I don't know, maybe. I mean, that's a question I actually never thought about, but it could be interesting.
Well, I mean, I'm not sure that from physical point of view, it's forbidden. I mean, you can imagine continuing the minimal models to generic central charges.
Sure, sure. But I mean, but the way that you classify minimal models usually is by having integer coefficients. So
yeah, because you assume
in fact, all of these integer case, they're not giving you, they're giving you rational central charges, but they're not giving you integer central charges.
Yeah, but I mean, you get integer k in conformal field theory because you assume from the start you have a minimal model, but that's if right. You allow for the spectrum to be infinite, you could have generic
sure.
k.
Sure, sure, sure. So I agree with that. So, but then what's the question?
Well, whether you see in your formalism the possibility to have non-integer k.
Well, again, let me put it this way. We certainly have formulae which are which hold at arbitrary k. I mean, we write down formulae just for could write down an instant function of Stokes data for specific values of k. So as I said, mathematically, it's very likely that I can just put continuous deformation of these things. Not very sure what would I mean by train series with an irrational number of train series parameters or a differential equation with irrational order. But, again, I guess probably you can make sense of these things, but it's something that I have not thought a lot about.
Yeah, for example, the spectral curve, I mean, you have polynomials, right, depending on k, but could you extrapolate to a non-integer k?
Well, these are Chebyshev polynomials, so they have a definition, but they have integer, well, there's integral definitions for the Chebyshev, so maybe, yes, but again, I'd have to look at the exact, I mean, when you write them down just in terms of the cosines, they really look like polynomials and nothing else. But when you look at their integral representations, maybe there's a way to write them down for arbitrary k. Yeah, could be.
Okay, thank you.
Sure.
I mean, certainly in terms of differential operators, I mean, the extension to rational things or even irrational things are pseudo-differential operators.
Yes.
So that part exists. But I don't know about the other stuff. More questions?
So yes,
Sorry, go ahead, Ricardo, if you want.
No, I was just going to say that, I think that mathematically, certainly you can define all these things, but I'm not sure what else you would gain.
More questions?
Yeah, Ricardo, can I ask a question?
Sure.
So do you think there's some hope to get the Stokes data for Weil-Peterson volumes as the limit of the Stokes data for minimal models?
Yes, I mean, I don't know if there's some hope, but that's certainly something that one would want to think of. Yes, definitely.
Okay. Thanks.
More questions? So I had one myself. So in your function set of the betas, is it maybe so that function can be understood as an integration of something over the moduli space, where you keep the length of the boundaries to be specified by the betas?
Yeah.
Really? So there are like explicit top forms which are integrated to give you those?
Yes.
I mean, can you say a little bit about what they are?
No.
Okay. Because I mean, there is a sort of maybe obvious possibility to try to see if they would satisfy geometric recursion. Because your output satisfies topological recursion, and we have this very general scheme that if you have something given by geometric recursion, when you integrate over moduli space, you automatically get topological recursion. So I was just wondering if they would be amenable. So that certainly the volumes are, as we know, right? So
Yes. Right. That I think that could be actually a quite interesting question. Because that would be an interesting question, because then you could make the same question for the Dawson function, where I mean, at least we have not done yet, but I mean, there should be. As I said, there's either something else changing the Weil-Petersons, or it's the trumpet that's changing. But if you can tell me that you can actually write down something which it's sort of trumpet independent, then that would be quite interesting, actually. Yes, that could be very interesting. Yes.
But so if you could say anything about how it's defined for the interior parameters of the moduli space, what one is looking for. I mean, is it sort of some kinds of counts of curves or lengths of curves or functions of lengths of curves or something? Because this is something we understand how to do with the geometric recursion.
Right. Yeah, we don't know. This Dawson function is very recent, from 2 weeks ago, maybe. So we basically haven't managed to do any calculations with it yet.
Ricardo?
Yes.
Yeah, if you mean that you just have to change the trumpet, as you say, it means that it's a kind of transformation.
Look, this is a guess. Huh? This is a guess. So again, this is 2 weeks in the making.
This would mean just that the combinatorics is the same as for Weil-Peterson, so it would just be the intersection number of the volume. And the trumpet is just a transformation which maps you to a reference guy.
I agree.
So probably some integral formula or something like that, which would just change the measure we put on the moduli space.
Yes.
I mean, and if you want to understand it, you just have to look at the 1-point function or 2-point function.
Yes, I also agree with that. Again, this is 2 weeks in the making, so it certainly looks much more plausible to me that what's happening is that there's a change of the trumpet and not a change of the underlying enumerative problem. But again, let's wait another 2 weeks to see if we can actually make this guess precise.
Mm-hmm. More questions? No? Okay, well, then let's thank Ricardo again, and
thank you very much.
Let's await the talk wrote backwards in 14 days, right?
That's right. Thank you very much.
Okay, all right. So thank you all.
Thank you.
See you.
Thank you.